Then I've been going to talk about algebraic factorisation systems already this morning, so you may already have a little bit of familiarity. So today I'm just going to talk about a few examples of category factors. So let's start with some motivation. The idea is that algebraic factorisation systems generalise factorisation systems. And the way in which they do this is by replacing property with structure. So if we have a square in our category, which we have this algebraic factorisation system, and we have a left map and a right map, then we ask, instead of the existence of a unique bit of the left map against the right map, we ask for a specified chosen lift, making these two smaller triangles commute. And also, because it's a factorisation system, we ask that every morphism in our category factors the left map and the right map. Okay? And so, rather than these maps, these left and right classes of maps, being morphisms with a certain property, we ask that they're going to be morphisms with a certain additional structure. Okay? So, in particular, the right maps are going to be morphisms with some kind of algebraic structure, and the left maps are going to be morphisms with some kind of co-algebraic structure. Okay, so that's what algebraic factorisation systems are about. And so on the other side of the title, we have these delta lenses. The idea is that they generalise split-lot migrations. What is the way in which they do this? Well, they relax this condition of requiring our lifts of our split-lot migrations to be Cartesian. Okay? So again, it's some sort of relaxing of removing the property, just looking at underlying structure. Okay, there's a little bit of history. The reason for delta lens, which may appear to be kind of a funny name, is because I was first introduced in computer science rather than category theory. I won't go into the name at all. But a couple of years after I was introduced, they were looked at by some category theory and characterised them as algebras for some kind of semi-modes. The only reason I mentioned this is because it was sort of what got me started at looking at things at the work that I talk about today. You'll see that they're actually algebras from one and another. But what I want to talk about today is actually showing that the delta lenses are the left class, are the right class of a algebraic factorisation system. And so because we already know this sort of interesting example where the split of migrations are the right class of an algebraic factorisation system, whose left class are the split coreflections, or rather the co-reflective adjunctions. Today we'll see that delta lenses can be seen as the right class, and that I'll introduce this notion of twisted co-reflection as the left class. Okay, so the delta lens is equipped with some additional structure, which I want to call a lifting operation. What does this lifting operation do? Well, it says that for every object A in our domain, every morphism computed like so, we have a chosen morphism lying above it. Okay? And so this morphism, this choice morphism, to satisfy some axioms. The first axiom says that, well, it's actually just a lift, so it lies above U, which is F. And the other two axioms are just saying that this lifting operation preserves identities and composition. Okay? And so this is what a delta lens is, and if we add this extra axiom, which is that these chosen lifts are all Cartesian, we recover exactly the notion of what a split of vibration is about. Okay? So, that's what it is, and these things can be assembled into a double category. Okay? So this double category will have categories as the objects, the horizontal morphisms will be functors, the vertical morphisms will be these delta lenses, and the cells, or these squares, are just going to be commuting squares of functors which preserve the chosen lifts. Okay? So exactly what you would expect. And so this double category of lenses has a forgetful functor just down to the double category of commuting squares, where we forget this extra structure, this lifting operation. And we can also see this double category of split of vibrations if we restrict to those which have this extra Cartesian condition. Okay? So they're delta lenses, and we'll see that we have this lifting operation here. What I want to tell you next is how this idea of lifting operation can be gradually generalised to the setting of double categories. This is what we do about this stuff. So a double categorical lifting operation is something defined by a co-span of strict double functors into a double category of squares, a subcategory C. Okay, so this double category has cells which are commuting squares in that category. And so what I want to call an LR lifting operation is just a family of maps of morphisms in our category C, which make this diagram used, and which satisfy certain horizontal and vertical compatibilities. Okay? So here UI is the image of a vertical morphism in our category L, and here VJ is the image of a vertical morphism J in our category R. And this is just a commuting square or a cell in this subcategory of squares, and this lifting operation is really a choice of these depending on this geometry. Okay, so what are these horizontal and vertical compatibilities? Well, they're just what we would expect them to be. We have the image of some cell in our double category L. We take the limit against J. If we paste that with this lower boundary here, that's just going to be the lift of this outer rectangle here. Okay? And likewise, we can do something in the vertical direction. The pictures that I've drawn here are just the compatibilities on the left, but we also have dual compatibilities that we can write on the right-hand side. Okay? So that's what lifting, what a double category lifting operation is. And so what we can also do is construct a double category whose vertical morphisms are somehow morphisms of which we will lifting operation. So if we start now with just double functor into the double category squares from some double category J, we can find this new double category. And what it's going to be is, again, we saw this in the talk this morning, the objects, horizontal morphisms are just coming from our category C. But now the vertical morphism is going to be pairs of a morphism in C equipped with a lifting operation against every vertical morphism in our double category J. Okay? And because it's a lifting operation, it has to be compatible with all the double categorical structure of this double category J. Okay? So they're the vertical morphisms in this new double category that we define. And now the cells are just going to be, well, things like this, which can use with the lifting operations of energy. Okay, so that defines the double category. And dually we can define something. So here we've defined everything in terms of lifts on the left-hand side or the right-hand side, I can't remember. But we can do it dually on the other side to get another double category, which we can define like this. And if we actually start with an LR lifting operation, like I presented on the previous slide, we obtain a canonical pair of double functors like this. Okay? So, if you look at this, you might think, well, this looks very similar to what I showed on the previous slide, the definition of the delta length. It was also some kind of morphism in the category equipped with some kind of lifting operation. And it turns out that this is actually an example of this double category that we're constructing. So, what can we do? Well, we can define a small double category J such that the category on the right lifts against this double category J is precisely the double category delta length. Okay, so this is going to be a double category which has three objects, which are just the posets 1, 2, and 3. So the point, the interval, and the component end. The horizontal morphisms are just all order-preserving maps between them. The vertical morphisms, they're generated by two vertical morphisms. This one here, which just includes the initial object into the interval. This one here, which includes the interval into the initial part of the postal pair. And it's generated by these two things, so we also have the composite of this with this as our vertical morphisms. Okay, so not very much we're asking for here at all. And the cells, well, there's just going to be three non-trivial cells. Okay, so this first one is just, well, we don't really need to worry about this, but this second one is encoding some kind of identity condition. This third one is encoding some kind of composition condition. Okay? So what we can say is that this double category of lenses that I introduced is precisely this this double category right lifting instruction against this very small double category J lens. Okay? So the idea is that, well, the delta lens is precisely a functor, so a vertical morphism in cat, equipped with a lifting operation against every vertical morphism in this double category here. So a lifting operation against this one. It's a choice of every A for every U, such that this outer square commutes. feed AU, which makes these small triangles U. Okay? And so these extra cells of this double category are really a way of encoding the axioms placed on this lifting operation. Okay? So I'll talk about delta lengths and how they can be seen from this thing. What's an algebraic factorization system? Let's recall what we used from this morning. Algebraic factorization system, well, it's this cospan of double functors equipped with one of these double R lifting operations, which satisfies two axioms. The axioms are that these induced double functors, which I just told you about previously, are actually isomorphisms. Okay? And the second one is that every morphism in our category C gives a factorization through the image of a morphism, a vertical morphism in L, followed by the image of a vertical morphism from R, which is universal in some appropriate way. Okay? So this first axiom here is saying, well, the L and the R are orthogonal to each other in some appropriate sense, and this second one is really saying that we have these factorizations, that the factorization system is talking. Okay, so there's this theorem of Bergman which says that if C is a locally presentable category and J is a small double category over this double of squares, then there exists an algebraic factorization system given by this cospan equipped with some kind of okay, that's good. As a corollary, we get that there exists an algebraic factorization system on cat, whose right class are these double category delta lengths. Okay? So because lengths of this form R or D J for some small double category, we can get a precise result. Okay? So I could stop there. Okay, we've shown that there exists an algebraic factorization system with right class delta lengths, but somehow this would be very satisfying because we don't know what the left class this factorization system is, and we also don't know how to factorize any functor into something followed by delta lengths. So what I want to do now is tell you exactly what the left class is and how to do the factorization and so on. So the left class is what I'm going to call twisted coreflections. Okay? What is a twisted coreflection? It's something I made up. It's going to be a split coreflection, which is something you all know about. It's just a coreflecting junction, which is given by this data. Okay? So a right adjoint followed by a left adjoint together with some co-unit. The unit is going to be an identity, natural transformation, and these equations are saying that this is a junction. Okay? So it's going to be one of these things with an extra property. Okay? I want to step through this property kind of slowly because it kind of seems very complex the first time you see it. The property is that if you have a morphism in our category B, such that when we apply the right adjoint, it's not equal to an identity morphism. Okay? If we have a morphism like this, it's not set to an identity morphism by a right adjoint. Then there exists a unique morphism of this shape. Okay? Going from X to the main of this morphism to the right adjoint followed by the left adjoint dot X, such that two axioms hold, two properties hold. Okay? So, what does it say? Well, it says that if you look at the naturality square for U, this is F of U, this is the naturality square for this covenant here, it's saying that there exists a unique morphism which is a retraction of the counit at X, and such that U is equal to the composite of U bar followed by the top of thing followed by the right hand side. Okay? So the reason I call these things twisted coreflections is because this is some kind of twisted square, some kind of morphism, a twisted arrow. Okay? But what about the morphisms which are equal to identities? What do they look like? Well, there's just nothing. We're not asking for any extra property of those. If we get sent to the identity morphism by our right adjoint, then we're not asking for the existence of any extra morphism. It's just going to look like this. Isn't that right? Okay. So that's kind of weird, but I'm going to tell you on the next slide or two how they can be sent as quite natural things. But we can form this double category of these things. We have a double category, again, of categories of functors. It's the horizontal part, whose vertical things list suppose, is actually quite difficult in this definition. So we really need a better way of doing it. So again, we get this, we get the function down to the algebraic squares of K, which factors through the split coreflections. Okay, and zero. Split coreflection with network. Okay, good. So, I've claimed that these things are the left class of this algebraic refactorization system. I should say, well, how do we lift something in this left class against something in this right class? And I can show you exactly how to do it. Here's a commuting square, a cat, such that the left thing has a twisted coreflection structure, and such that this right thing has a delta band structure. How are we going to, and if we're going to define this function J, how are we going to define the image of some morphism in U, in B, how do we get its image in C, using this extra structure that we have on these boundary morphisms here? Well, because we have our Bryce joint Q here, we can lift it up to a morphism here. And actually we have two cases. We have the case where Q sends this to an identity morphism, and the other case where it sends it to a non-identity morphism. I'm just going to work through one of those cases. So if it gets sent to a non-identity morphism, well, then we have this coordinate square together with this unique morphism named this thing unity. Okay, so far so good. Now we can apply H and K to get, well, this morphism here in C via the functor H, and this square in D via the functor K. But we know because this square commutes that these two things are just equal to these two things here. And now we can use the delta band structure to lift this section of traction and lift this morphism here up to something in C. And now finally the image of U under this functor J that we're trying to construct is just going to be the composite of this thing followed by this thing followed by this thing. So we get our lift. Okay. Now all I've done here is define how to lift this particular morphism of one of the classes. I haven't shown you how to see that this is respects identities, respects composition, that's a functor that preserves that respects these horizontal and vertical compatibilities of both of these double categories. And you can imagine trying to do this with this definition is immensely complex and tedious yet not straightforward. So we need to do something better than that. And so what I want to do is introduce a diagrammatic characterization of both these left and right classes. So let's start. So this is going to be the most important slide. So the left class, these twisted coreflections, these are junctions, coreflective junctions with an extra property. How do we characterize this extra property? How do we introduce this immensely complex definition to something that's simple? So let's start with this junction, this underlying junction. What we can do is look at this canonical identity objects functor from the underlying discrete category, defining the same set of objects as A. Now, we can pull back any coreflective junction, we can pull back the right adjoint of any coreflective junction along any functor to get a new adjunction. Okay? A new coreflective junction. So we always get the square for any adjunction, for any coreflective adjunction, I should say. And so X is going to, because it's a pullback, it's going to have the same objects as B, and this is going to be an identity objects functor, and the morphisms are just going to be those if they just sent to the identities we get the right adjoint. Okay? Now, we can forget about the right adjoints. We can just look at the underlying commuting square of left adjoints. Okay? Actually, these two things are in bijection. Because adjoints with a discrete category which are coreflective are just in bijection with initial functors, like this. So far we can do all of this with just any adjunction at all. For any coreflective adjunction. The property that characterizes these twisted coreflections is precisely to ask for this square to be a push out. Okay, that's all we require. And so this push out is actually a really nice push out. We can construct it explicitly. Ordinary when you do push outs in category theory, you can do quotients and co-equalizing and you can find like strings of morphisms. This just has very simple properties, very simple characterization that I won't tell you today. But it's a very easy thing to say. And so these are how you characterize the twisted coreflections And actually, if we go the other way, if we started with a square like this, we can construct a canonical twisted coreflection structure on F. Okay, so these push-out squares of an initial functor from a discrete category along an identical object functor are completely the same thing as these twisted coreflections. I found this quite amazing when I first figured out. I managed to produce some very complex definitions of something just like push-out squares. Okay, these delta lenses also have this nice diagrammatic definition in CAT. It's just going to be a functor together with an identical objects functor which composes to be in a discrete operation. The idea is that this category Y is the same objects as C, and whose morphisms are just which chosen leaves which determine by this different operation. And again, we can go back the other way. If we have any diagram like this, we can get a unique or a canonical delta lens structure on this functor G, and these things are a one-to-one correspondence. Okay? Great. How are we going to use this to describe the rest of the structure of this algebraic factorisation system? Well, let's go back to the lifting that I showed you before, which was quite involved. And how do we do this in a simpler way using this new categorisation? Well, again, we have this coreflection, this delta lens. We can replace that by this triangle here that I showed you on the previous slide, this push-out square that I again showed you on the previous slide. And we can construct the lift in 3 simple steps. The first step is to use the universal property of discrete categories and bijective object functors to construct a unique functor like this, making this diagram cute. The second step is to construct a unique functor L using the universal property of the comprehensive factorisation system, because this outer morphism here is a discrete operation, and this morphism here is an initial functor. Okay, so they're the two classes of the comprehensive factorisation system. So we can construct this canonical lift here, like so. And then finally, we use the universal property of the push-out to get this functor J from B to C, making these two smaller triangles here. Okay? So we've reduced something that was sort of much harder to do very explicitly with these explicit definitions to something that's very easy to state using the universal properties of these known functors in CAT, essentially. Okay, great. And so, again, showing all these vertical and horizontal compatibilities of these double categories, again, it's much easier to do using these universal properties. Good. What about the factorisation of this factorisation system? Well, take a functor, precompose it with this identical objects functor from the discrete category, look at the composite of that thing, and take its comprehensive factorisation. And then finally, take this push out, and we get exactly what we want. Okay? This top square is a push-out square of an identical objects functor from the discrete category along an initial functor. So L of F has a twisted coreflection structure. And this bottom thing, well, this is going to be an identical objects functor because they're stable on a push-out. This here is a discrete operation, so this is a triangle which has a delta length structure on R of F. Okay? This J over here is just this co-product of most light spectrums. Okay, great. So we have code-free twisted coreflection on our functor F. We have the free delta lens on our functor F. And these, if we actually make some choices here, these give us the co-product on the arrow code CAT, whose co-outputs are twisted coreflections and delta lenses respectively. Okay? So that's all very nice. That gets us back to the more traditional definition of an algebraic factorisation system in terms of the compatible monad and co-monad pair. But yeah, okay, so now again, here, there's an algebraic factorisation system on CAT, given by this co-span of double categories getting down to squares in CAT, whose left pass are these coreflections and whose right pass are these delta lenses. Okay, so for every square like this, where there's twisted coreflections and delta lens, we can construct this canonical lift. We have a bunch of these isomorphisms. Actually, of the theorem, this is the hard part to prove, is that these first two isomorphisms hold, but it's not really that bad. And again, we've just shown how to do this factorisation. I'll just say some future work. We could consider how to generalise this double category with lifting operations where we replace the double category of squares in the middle here with some arbitrary double category, maybe with some certain properties. And finally, we could ask for this relationship between this factorisation system I've considered and so-called co-reflective factorisation. look kind of artificially similar when we use details in constructive factorisation. But I'll stop there. Thank you.
Any comment?
Right, so how much of this can be done like internally, like if the algebraic factorization system gets heat?
Yes, there ought to be, but I'm not sure at the moment. I mean, again, the hard part is this part here, showing these isomorphisms. And when I do this proof, I really need to use that we're working in cat rather than on cat E. And so I'd really like to know if there's some kind of internal way of proving these isomorphisms here, like just in cat E, but I'm not sure how to do that.
Do you have any, like, do the fiber objects with algebraic factorizations? Nice description of that.
So the fiber objects are the objects which appear as the name of a vibration into the term, right? But here we see that every delta lens into the terminal object. So every
Code fiber?
I don't know.
Hi Bryce, thanks for the talk. You know what's sort of thought about this stuff, but so there's the comprehensive factorization system, that's the initial followed by discrete off vibration.
Yes.
It seems like in the end, the proof was quite sort of categorical in nature, like it uses factorization system and some basic properties to push out some things.
Yep.
So I was wondering whether you could sort of go a step further and say, well, why don't you just take some arbitrary factorization systems and properties, and could you make it work not just with a comprehensive factorization system, but like...
Yeah, that's an excellent question. Really want to be able to just take any orthogonal factorization system as a starting input together with some idempotent co-wire, which in some sense is giving you the bijection objects things, or equivalences of that idempotent co-wire, and do all the same stuff. Again, the sticking point is really being able to show these isomorphisms here in a nice way. Yeah, that's really the way one could approach the real example of this way.
Was there any question?
I was going to ask Matt's question. Matt asked it for me.
I understand there are no more, so let's thank Bryce.